as we move into our last section of Chapter 8, the challenge is we start looking at things three-dimensionally. We're looking at volumes of solids, and so we have to take our two-dimensional papers and be able to look at them in a three-dimensional way. Our first topic in this is going to be talking about different shapes of cross-sections. If we were to use our pictures of our functions that we've had and use those to create a three-dimensional solid, creating different shapes as cross-sections. So to visualize this, we're going to utilize this link here as this loads. And what this is going to do for us is allow us to look at what you're looking at here. Let me lead you through. On the left-hand side, you can see we've got this blue graph. It looks kind of like a parabola, or part of a parabola we can see there. The red graph, probably a square root of x graph. And what we can do is pick somewhere in there to create these cross sections. And so what we're going to see in this section is they'll give us a shape to be formed. And so this blue bar that you see on the left-hand side is also shown on the right. The right is going to show us the more three-dimensional view of what's going on. And so if we were to maybe say that the cross sections of our solid formed between those two functions were squares, where the edge of the square was parallel to our x-axis and bounded by those functions, we would see that as one of our cross sections. And what this little animation is going to allow us to do is, okay, so if I were to fill in all the way from where those two functions intersected, which we would have normally just filled in the area between those, and now we're looking at a volume, that would have started, it looks like, at 0 and gone all the way to 1. And so what I can do is I can add in some more squares to help me fill in, and all of my cross sections in here are going to be the shape of a square. And we can fill this in not only from where it's at, but all the way across here, again, kind of filling in. And if I take those away, you can see it's just adding in a bunch of squares. And what happens, the squares have to have the same base and height, and so you can see that it gets tall there in the middle when the base is the widest, and continues then to become smaller squares as the base becomes shorter, all the way down there. And again, if I fill this in, let's go all the way out to 1. If I fill this in with a ton of squares, you can see that it fills it in to be a solid object. And what we're going to do is find the volume of that solid, which would be adding up the areas of all of those little squares that we have in there, or using the idea of integration. And as we can kind of rotate this around, you can see a little bit of that solid in there, formed by all of our squares. So that is what we're doing, is seeing these two-dimensional pictures. Now we're going to look at them three-dimensionally. So let's go back to our notes here and see then what's going to happen to find our volume. So if we're using the idea of adding up a whole bunch of areas of squares, that's again the idea of integration. So what does that look like when we're finding volume? So when all the cross sections are filled in, we have the volume of our solid, and if we can find the volume using the integral from A to B. Now, this is not going to mean much to us at the moment, but it's going to become very important as time goes. We're going to pick our A and B, the interval, in the direction that our cross sections are stacking up. So is that going down our x-axis, or is that going down our y-axis? Our function will be an area function. Whatever the shape is that our cross-section is will help us determine what that area function is, using our geometric area formulas for like a square or a triangle or a circle. And then picking our variable of integration, again, will match the direction that our whatever our cross-section is stacking up. So is it going down the x-axis or the y-axis? And so we would say dx or dy, depending on which axis our cross-sections are stacking up. And another note is that that does impact our area formula. We want our area formula to be written in terms of that variable. So if we were to be stacking up our cross-sections down the x-axis, we would want our equations written in terms of x, or our normal y equals something in terms of x. But if we were going down our y-axis, we would want it to be in terms of y, so we would need to rearrange our equations so that they said x equals something in terms of y. And understanding what fills in those three parts of our integral here is going to be very, very important heading forward through this whole section. So make sure you spend some good time understanding the three different parts of our integral. Okay, so here is an example. A pyramid that is 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross section, and that's going to become very important to us over all of these problems, is what's the shape of the cross section? Each cross section of the pyramid is parallel to the base and is square. Find the volume of the pyramid. So one of the things we're going to want to always do is just analyze our cross sections to start with. So what you'll always see me do is then just take one cross section just to represent all cross sections and kind of identify for myself what I know about that cross section. I know it is a square. I don't know exactly how big because it kind of depends on where in the pyramid that it would be located. Obviously closer to the top or the peak of that pyramid, it would be a smaller square. As we head towards the bottom, a bigger square all the way up to a 3 by 3. But what I know about squares is that they have the same base and the same height, which means I can identify its area as the equation, the side length squared. And so that's what we'll do with each of these objects, identify the cross section, know what the functions are telling us then about the dimensions of that to be able to formulate an area formula for that cross section, and then translate that into our volume integral. So given that information, the volume of that pyramid, the volume of the shape that we see being formed, would be summing up all of the squares that we could stack up, and we are stacking them up along our x-axis, going from starting here all the way up to 3. So that would be our bounds on our integral, starting at 0 up to 3 on the x-axis, again, in the direction that our squares would be stacking up in there. And then after that, we fill in our area formula, which we identified as x squared. And again, we are doing this down the x-axis, so dx. And those should mesh together. We shouldn't have something in terms of y dx in there. And so then if I were to just do that, now that one would be a really easy one for us to do with our antiderivative, 1/3 x cubed, evaluated from 0 to 3. Plugging in our bounds here, 3 cubed minus 1/3, 0 cubed. And we would find out that we have a volume of 9, and it is in volume, so, and they said it was meters up at the top, so meters cubed. All right, second example. So kind of, again, changing our shapes here. It says the region R, which is what you're looking at there, is bounded by the relation x squared plus y squared equals 4. That's the equation of a circle. We see a circle. Is the base of our solid. For this solid, each cross section is perpendicular to the x-axis is a square. So again, it tells us about our cross sections. Find the area of the cross section and the volume of the solid. I do have, again, a link to a visual on this one. So if we were to go here and look, I found one that has a circle. We are going to do squares on this one. Let's see if I can make this full screen for us. And as we move this across our picture, you can see it's showing the square gets bigger as the distance gets the longest on the base there. We've got smaller squares as the base of the square gets smaller, all the way across our picture. And then we've got this trace function on here that allows us to then show all of those, totaling it up, showing the solid that ends up being formed here. As I drag this across, it shows all of those squares, making this large dome-shaped solid all the way across there. And I can go back and fill in the ones that we kind of missed back at the beginning. And this solid object then is what we will eventually be finding the volume of. So if we go back to our notes here. So if I just, again, pick one place along here, maybe representing here, and I'm going to use that here in just a second. So if we were to consider one cross section, again, they tell us that they are squares. This side right here is represented by the red line that I drew in our picture. And our square is extending vertically from that or towards us. from that. And so the challenge on this is to decide what is the length of that base of that square. And we know it's a square, so both sides are going to be the same length once we figure out what that is. And so what I want to consider is, first of all, about halfway through that would be that dot right there. But let's talk about what's forming our picture here. And as I'm stacking these up, I am going to be stacking these squares up with respect to our x-axis. So what I did is I took the equation, the x squared plus y squared equals 4, and looked at it in terms of y. So if we were to solve that for y, remember that we would be square rooting, so that gives us the plus or minus. So that would be our equation that we had at the beginning, x squared plus y squared equals 4 in terms of y. But that represents the two halves of the circle, top half being the positive square root, and the bottom half being the negative square root. So if I were to just kind of consider half of that from 0 up, that length would be the square root of 4 minus x squared, which means this entire distance would be double that, or 2 times the square root of 4 minus x squared. And the reason I looked at it that way is if we look at just adding the two pieces together, which is not exactly what's happening, it looks like it would be 0, because the square root of 4 minus x squared minus square root of 4 minus x squared would be 0. But it's really 2 of those lengths. And so I find the side length of that being 2 times the square root of 4 minus x squared, which then gives us an area for our square, again, side length, 2 square root of 4 minus x squared, squared, or 4 times 4 minus x squared, which we could simplify to 16 minus 4x squared. So then transitioning into our volume, let's talk about our bounds for integration. So I am moving along my x-axis, so I would want to look at where we start and where we stop along our x-axis. Going back to what I know about a circle, right here is the radius squared, which means our radius is 2. So this is going to start at -2 and go to +2, which would be my bounds of integration, -2 up to 2. Put in my area formula, 16 minus 4x squared. And again, we're doing this down our x-axis or in terms of x, so dx. And again, I could do this by an antiderivative, which would have been 16x minus 4/3 x cubed, evaluated from -2 to 2. And to just kind of speed us along here, that comes out to 42 2/3 units cubed, because again, we are talking the volume of the solid. All right, so moving on to our next one, it says, and we're going to look at this one in a couple different ways, changing the shape of our cross sections. But it talks about a solid that lies between the plane perpendicular to the x-axis, x equals 0 and x equals 4, and the cross-section perpendicular to the x-axis for y equals this negative square root of x and y equals square root of x. And this picture is kind of turned on its side here, but the two equations that they gave us, the negative square root of x would be here, and the positive square root of x then would be this side of it. And our circles are falling between that. So again, if we just zero in on one cross section that's falling between those two functions, one radius on this, because they are circles, so as we move towards our area formula, we do want to talk about the length of the radius, would be the square root of x. And it's a distance. Radius is a distance, and so I'm going to go with the positive square root of x. Doesn't matter which direction, which means the area of that circle, pi r squared, r being the square root of x squared, would be x pi. So then talk about where this is totaling, and they gave us this, is that we are going from x equals 0 up to x equals 4. So I'm going to add these circles or stack these circles along our x-axis from 0 to 4. And that tells me my bounds of integration and also the variable we're using here. So from 0 to 4, our area is x pi along our x-axis, so dx. And if we just, again, we could do our antiderivative for this. Kind of good practice for us would be 1/2 x squared. Pi is just a constant. And evaluating that from 0 to 4. Would give us a total volume of 8 pi. Okay, so sticking with that same function, but changing the shape of our cross sections. So again, we're going from 0 to 4, but this time we're using cross sections that are squares, and their base is in that xy plane. So if I would consider that again, always zooming in on just one cross section, its base would be connecting those two functions together from negative square root of x to positive square root of x, which means that the length of one side of our square would be 2 times the square root of x. From here to here just being the square root of x, this would be the same on the other side, doubling that, we get 2 square root of x. And so then my area, again, it's a square, so the length of the side, which is 2 square root of x, would get squared, which would give me an area of 4x. And same bounds of integration, because we are moving our squares or stacking our squares up along the x-axis. And we are going on the x-axis from 0 to 4. Our area is 4x in terms of x. Using our antiderivative here, we would have had a 2x squared evaluating from 0 to 4. Plugging those in, we get a volume of 32 units cubed. Okay, the next one in the picture actually does not show this one correctly. It says the cross sections are squares with the diagonal in the xy plane. So instead of that picture right there, what instead we should be showing is this line that is in the xy plane is the diagonal of our square this time. And so we know from our previous conversation that the length of that diagonal, half of that being, x square root of x, this side would also be the square root of x. So as we were to examine one cross section, we know that its diagonal is 2 square root of x. So through our Pythagorean theorem or through special right triangles, however you want to attack this, if I were to call maybe the two sides of our square a squared plus a squared equals 2 square root of x squared, I can easily find that a is going to be the square root of 2x. Therefore, again, using that to find the area, so my side length is the square root of 2x squared, gives me an area of 2x. So then putting that into our volume formula, same direction, so still going along our x-axis from 0 to 4, our area is now 2x in terms of x, which gives us an antiderivative of x squared evaluated from 0 to 4, or a volume of 16 units cubed. Last one I want to look at again is the same section, but this time they say that the cross sections are equilateral triangles with their base in the xy plane. So again, instead of it being a square, we would have an equilateral triangle. So here's my base of my equilateral triangle. So we know again from our previous conversation, since this is connecting up to our square root of x function, this would be the length of square root of x. This would also be the length of square root of x. So as we examine one cross section, its base would be 2 square root of x. So again, this has a little bit of geometry conversation to be had here, knowing that the length of the base of that equilateral triangle is 2 square root of x, which some of you may remember there is a area formula for the area of an equilateral triangle, which I'll remind you of here in just a second. But we can also get there by just knowing what we know about right triangles. So then half of that would be just the square root of x, which would allow me to find the height using my Pythagorean theorem. Through Pythagorean theorem, let's see, height squared plus square root of x squared equals 2 square root of x squared. Our height is going to be the square root of 3x, which makes our area of a triangle 1/2 base times height. Okay, and going through that, 1/2 times 2 is 1. Square root of x times square root of x is x, and that square root of 3 will stay inside, so we'd get x square root of 3. Same direction that we are stacking up our triangles down to our x-axis, so we're still integrating from 0 to 4. Area of our cross-section is x square root of 3 in terms of x. And again, I could go to my Math 9, I could do my antiderivative here, which would be what? Square root of 3 over 2x squared evaluated from 0 to 4. And it comes out to be 8 square root of 3. All right, your assignment then is on page 410, 1, 3, 5, 6, 39, and 41.